Okay, so what we need to talk about now is the vibrational and rotational spectrum you get from molecules. And again, our model is going to be a diatomic molecule. Before we do that, I want to take a few minutes and talk about reduced mass. You may be familiar with reduced mass, but it's good to review where it comes from and so what it means. So we are working with a diatomic molecule, so we're going to have two masses, mass 1, mass 2. They're separated by a distance r, which I'm going to call r. So r goes from mass 1 to mass 2. Now there is a center of mass for the system. Now let's say our origin of our coordinate system is down here somewhere. So it locates mass 1, let's call that R1 from the origin. The center of mass is located at RCM from the origin, and then we have R2 from the origin to mass 2. Now the center of mass coordinate, by definition, it's equal to mass 1 R1 plus mass 2 R2 divided by the total mass. So that's really our definition of the center of mass. Now, notice up here that if I take R1 plus R, it's equal to R2 because I end up at mass 2. So R1 plus R equals R2. And just to remind you, again, R goes from mass 1 to mass 2. Now, where I'm going to go from this in the end is I want to write the kinetic energy. And I want to write the kinetic energy in the end as a function of the velocity of the center of mass and then of one of the masses relative to the other. So I'm going to want to write, I want my kinetic energy as a function of r center of mass dot, so the velocity relative to the center of mass, and r dot. That's what I want to write my kinetic energy in terms of. So I have this. This would give me R2 is equal to R. Oh, I have that. R2 is equal to R1 plus R2. Okay. So now from this equation, I can write M1 plus M2 R center of mass is equal to M1 R1 plus M2 R2. Now I want to get rid of R2, so that's going to equal M1 R1 plus M2, and R2 can be written as R1 plus R. Put everything with R1 on one side, bring everything else to the other side of the equation. I'll have M1 plus M2 R center of mass minus M2 R equals M1 R1 plus M2 R1. So I can see I can write R1 is equal to R center of mass, because I can pull this out, I'm sorry, M1 plus M2 R1 there. R1, when I divide both sides by M1 plus M2, I get R center of mass here minus M2R over M1 plus M2. Now I could do the same thing and get rid of R1 and write R2 in terms of these, and you'll get R2 is equal to R center of mass minus M1R over M1 plus M2. And you can try that and see that you get that. So now my kinetic energy. My kinetic energy, which is 1/2 mass 1 R1 dot squared plus 1/2 M2 R2 dot squared can be written, since I can write R1 and R2 like this, and then if I take the time derivative, I get this. I'm going to replace R1 with this up here, R1 dot with this, and R2 dot with this, and then of course I have to square things. But I'll leave it to you to find that you can write it like this in the end. Okay, now that means you can write the kinetic energy as the center of mass, the velocity of in terms of the velocity of the center of mass squared times the total mass. So this term there, plus this other term. So if our origin was at our center of mass, so if we said our center of mass is 0, if origin is at our center of mass equals 0, then we have the kinetic energy is just so what we've done is we've taken this two objects rotating, moving around in origin, and reduced them to one. So this acts like one object where you have your center of mass, you have an object out here, a distance r from the center of mass, and it has a mass of m1, m2 over m1 plus m2. So we call that the reduced mass mu. So we've simplified this problem from two particles rotating around the origin to one particle with this reduced mass. Just easier to handle mathematically. Okay, so there's where reduced mass comes from. So now let's go on and talk about rotational and vibrational spectra. So first we're going to talk about rotational. So we know in atoms, when electrons make a transition, let's say from the n equals 2 down to the n equals 1 level, say in hydrogen, you get a photon, and the energy of that is on the order of EVs. We're going to find out that, of course, if you have charged particles like the nuclei, for example, moving, they may accelerate. They accelerate maybe by changing their rotational energy. They can also produce photons, or they can vibrate back and forth at a certain frequency, and if they change that vibrational pattern, they can emit photons. So electron transitions are in the realm of EVs. So that's change in electron energy, change in the energy. The change in energy for rotational, we'll find out is much smaller. It's on the order of 10 to the negative 3 EVs. And for vibrational motion, the change in energies are on the order of 1/10 of a EV. Okay. So let's think about the rotational. energy. So again, we have this molecule has mass 2, mass 1, there's the center of mass, but we're going to treat this as if it's a particle with a reduced mass. It has an energy due to rotation, 1/2 the moment of inertia times theta dot squared. We call that omega when you had physics 182. But you can also write that as L squared over 2 times the moment of inertia, because L for circular motion would be I theta dot. Okay, now just with the atom, we're going to assume our angular momentum is quantized for our molecule. We're going to use that L squared, big L squared, angular momentum squared, is L little l times L plus 1 h bar squared, where L can be 0, 1, 2, 3 little l. We require for a transition if you look at what transitions are allowed, we have to have a change of L of plus or minus 1. So our energy of rotation, written in terms of angular momentum, would be L squared, L times little l times L plus 1 h bar squared over 2 times the moment of inertia. And just to remind you, for L is 0, you get rotational energy of h bar squared over 2I. No, you wouldn't, you get 0. Take that back. Okay. So now let's think about our diatomic molecule. Let's say we have, for example, H2, but let's just say we have the same atom for both masses. M. The reduced mass in that case, which is m times m plus over 2m, is just m over 2. So let's assume that's what we have. If it's hydrogen, this would be the mass of the proton. So if it's H2, we'd have mp over 2 mass of the proton, which would be half of 1.67 times 10 to the negative 27 kilograms over 2, which would be 8.35 times 10 to the negative 28 kilograms. Okay. Now let's think about the rotational spectra. So you have to, let's say we get a change from, in our angular momentum of our molecule, we go from L up to L plus 1. We get an increase. Or maybe it makes more sense to you, let's go from L plus 1 to L. Okay? Either way. I think I'm going to change that. I think I am going to go. Let's do the transition from L to L plus 1. What's the change in the rotational energy? So initially, we have L plus 1. Just to remind you, our rotational is h bar squared, L times L plus 1 over 2I. I being the moment of inertia. So For L plus 1, we'll just put L plus 1 wherever we have L. So we have h squared over 2I times L plus 1 times L plus 1 plus 1. And then minus what we started with. So h bar squared L times L plus 1 over 2I. So I can pull out the 2I and the h bar squared. And then what do I have up here? I have L plus 1 times L plus 2. So I get L squared minus or plus 3L plus 2 minus L squared minus L. So I get h bar squared, this is an I, over 2I. The L squareds up here cancel out, and I have 2L plus 2 left. I'll pull out the 2. No, if I pull out the 2, I have 1 here. Pull out 2, L plus 1. So I get a change. This was going from L to L plus 1. Okay. So let's keep this result. I'm going to write that on a new piece of paper here. When we have L to L plus 1, the change in rotational energy is h bar squared over 2I, but I have that I on top that'll cancel out this one, so then it's L plus 1. So let's keep that. And I'm going to save a space here because now we want to look at the case where we go from L to L minus 1. So we go down 1. And it's exactly what you think. We put in the final, which is going to be L minus 1 times L minus 1 plus 1, h bar squared over 2I, minus L times L plus 1, h bar squared over 2I. So this is L times L minus 1. This would be just L minus 1, h bar squared, 2I, minus L times L plus 1, h bar squared, 2I. Pull out the h bar squared, 2I, and I have L squared minus L squared minus L. So I get that these L squares cancel out and I get minus 2L. So we said if we went from L to L minus 1, our change in our energy, negative h bar squared over I times L. Okay, let's do an example. In a transition from first CO, transition from the L equals 0 state to the L equals 1 state. Has an energy difference of 7.62 times 10 to the negative 23 joules, which is 4.76 times 10 to the negative 4 electron volts. So that's something we can measure, how much energy required to make that transition. So let's use this to find the equilibrium length. Or get an estimate for it. So the equilibrium length is, here we have our carbon, here we have our oxygen. It's that distance when they're in equilibrium. They like to be at that distance. You remember when we looked at the potential versus a distance between the ions, there was some equilibrium. Okay, now where is that going to come into play? That's going to come into play in the moment of inertia. So the moment of the inertia is going to be, we act like this is one particle around the center of mass and at the equilibrium length. So for a particle, just a single particle, mass m, going around in a circle, distance r, the moment of inertia is mr squared. So we're going to use r naught squared as the distance, this one mass, and it's the mass, the reduced mass. Okay. So what do we have? We have our change in rotational energy, which is this, is equal to what we have. We're going from L0 to a higher L. It's this. Oh, and what L do you put in here? You put the L you start with. That's that L. That's that L. The L you start with is this L that's in this formula. I forgot to mention that. So we would have L is 0 initially. So then we have h bar squared over I, and I is okay. Now we need the reduced mass. The reduced mass is, let's do it in U. The carbon mass is 12U. Oxygen is 16U over 12 plus 16. So we get 6.857. And 1U is what is 1U? See, 1U is 1.66 times 10 to the negative 27 kilograms. So this would mean, this makes this 1.14 times 10 to the negative 16 kilogram, negative 26, I'm sorry, 26 kilograms. Okay, I just need to stick things in now. I need to solve for R naught. R naught is going to be h bar squared over mu times the change in rotational energy and the square root of all that. So it's going to be h bar in EVs per time seconds is going to be 6.582 times 10 to the negative 16 electron volts times seconds. So that's the square root of h bar squared over the square root of 1.14 times 10 to the negative 26 kilograms times our rotational energy, which is 4.76 times 10 to the negative 4 EV. Let's see, I'm going to change my mind. I'm going to put everything in SI units. R naught is 1.055 times 10 to the negative 34 joules per second. That's the h bar over the square root of 1.14 times 10 to the negative 26 kilograms. And our energy in joules is this. 7.62 times 10 to the negative 23 joules. And let's see what that comes up with. It comes up to be 1.13 times 10 to the negative 10 meters. So that'd be 1.113 nanometers. Okay. Well, here we have rotational energy and how we might use it in an example to do something useful. So we'll keep these in mind. We'll come back to those. What we're going to talk about next is vibration.